parameters, 4 line parameters I have specified: shunt conductance, resistance, inductance, and capacitance. In that, right now we are dealing about inductance in a circuit. So inductance, so a transmission line may be classified into many categories. It can be a single phase transmission line, or it can be a 3-phase transmission line. And in 3-phase itself, there are many combinations. It can be a symmetrically spaced 3-phase transmission line. It can be a unsymmetrically spaced 3-phase transmission line. It can be a transposed transmission line. I have taught each and everything in detail. The inductance estimation of each and everything have been dealt very successfully. Right now, you all know that inductance estimation is very, very simple. Am I correct? So the estimation starts with the important term called flux linkage. Flux linkage, if you are able to evaluate in any system, you can evaluate easily the inductance. So inductance is equal to flux linkage divided by current. That is what the thing. So each and every system, the flux linkage has to be estimated. If you are able to estimate the flux linkage, then it will be very easy to estimate the inductance in the system. Right? So today in this class, what we are going to learn is that we are going to learn about another important aspect of transmission line. It is going to be a double circuit 3-phase transmission line. So far in the last 2 classes, what we have learned is about all a 3-phase transmission line, 3-phase transmission line. So today in this class, I am going to talk about a double circuit 3-phase, double circuit. So can anybody have what it might be? Double circuit. Any guess? Right. It is very, very simple. I will come to the point. So far, whatever we have discussed, each and every phase has only one single conductor. Single conductor. If you look at 3-phase inductance estimation, all had a single conductors for each phase. So now, what we are going to learn in double circuit line means we are going to learn about a double circuit line with 2 number of conductors per phase. That's it, very simple. So per phase, it will have 2 number of conductors. Okay. So let me start with the first structure. So you may take down. Inductance of double circuit 3-phase line with unsymmetrical spacing but transposed. Right? So the only difference is in the earlier thing, what we had is that we had 3 conductors. So, I mean, for a 3-phase line, each phase has 3 conductors. So let me start with the position number 1, because in transposition, for a fixed duration, there will be 3 different numbers, 3 different positions each and every conductor will occupy. So I have considered 3 different positions. Position number 1. So how the conductors are arranged, I am going to list out. So you all know that each and every phase will have conductors. Let me assume that X, Y, Z are the conductors for each and every phase. That is it can be a R phase, Y phase and B phase. right? So now, if you look at this, only one conductor I have represented it. Am I correct? This can be for R phase, this can be for Y phase, and this can be for B phase. Let me assume that. So, but whatever the title specifies, it is a double circuit three-phase transmission line. So, double circuit in the sense, each and every phase is going to have two number of conductors. So, the conductor arrangement, so the first conductor arrangement alone we have included. The second conductor arrangement, X dash, Y dash, and Z dash. Okay, these are the possible first conductor arrangement. That is, this is for again R phase, this is for again Y phase, this is for B phase. Right. So for R phase, there are two number of conductors. You can look at this, X and X dash, X and X dash. For Y phase, there are two number of conductors, Y and Y dash. For Z phase, there are two number of conductors, Z and Z dash. So the positions are arranged because there are three possible positions you are going to see. So this is a first ideal position for the double circuit three-phase line. Right. Now, let me assume that the conductors are identical in nature. Identical means it is similar, identical in nature. And if you look at the phase, R phase, X and X dash are both responsible for carrying power in the R phase transmission line. That means that these two conductors will be connected in parallel for carrying the power. Am I correct? So two conductors are connected in parallel to carry the power. Very simple. Just look at this. I'm just drawing the diagram. This is an R phase incoming line. It is divided into two lines. This is an receiving end. This is sending end. So sending end, the power is divided into two lines and it is transferred. That is what? The double circuit line. So these two lines are connected in parallel. That is R phase transmission line is connected in parallel. So this is for, let me assume that R phase. Similarly, there will be again one more line, two circuit line for Y phase. Again one more two circuit line for B phase. Now can anybody say what is the advantage of this transmission line? So each and every conductors are, each and every phase is provided with two conductors. The major advantage is that the power carrying capacity of the transmission line is increased. The power carrying capacity will be more. This is a first aspect. Second aspect, if any one of the line is damaged or if it is experiencing a fault, then another one line can be used for transmitting the power. Let me assume that, say, if you take two double circuit line, say this line is damaged, some problem is there with respect to this line, then this line alone can be used for carrying the power. Very simple. So the reliability of the system will be more in this kind of double circuit three-phase transmission line. So everyone knows about reliability. Am I correct? Reliability in the sense, continuously providing electricity, we call it as a reliable system. It is reliable, whatever the things happening in the system, it is reliably providing electricity. right? Now, what I would like to majorly convey, this X and X dash are connected in parallel. Similarly, Y and Y dash are connected in parallel. Z and Z dash are conductors connected in parallel. Right? Now it is over. So if, let me assume that I'm just asking you, this is an inductance of L1. This is inductance L2. Can anybody say what is the equivalent value of inductance? L1, L2? Good, very good, very good. So now, one more example I would like to give you.
5 L1 plus L2.
Yes, yes, good. Now this is L. This is again L. Tell me what is the inductance? Equivalent inductance.
L by 2, sir.
L by 2. Am I correct?
L by 2.
L by 2. So with this, I would like to. So in a parallel circuit, say for example, I am saying that the conductor X is identical. I mean, all the conductors are identical in nature. That means that X is similar as that of X dash. X dash. That means that whatever the inductance provided by X will be equivalent to X dash. So let me assume that Lx is the inductance of conductor X. I am saying that conductor X and X dash are connected in parallel, and it is having an identical structure, and the conductor is also similar. So now, if I am assuming the conductor X inductance as Lx, so X dash will also be Lx. So these two are connected in parallel. Can anybody say what is the equivalent inductance per phase conductor?
Lx by 2, sir.
Lx divided by 2. Right? So with this, I would like to start the derivation. So what I am going to do is that I am going to consider only this X for deriving the inductance. Since if I am able to derive the inductance of X, it will be same as that of X dash. And if I know the inductance of X and X dash, I can easily derive the inductance per phase in the sense X and X dash are responsible for R phase inductance. These two are connected in parallel. Then per phase inductance can be calculated by Lx divided by 2. If Lx is assumed to be the inductance of conductor X. So now my ultimate aim is to derive the inductance of X conductor. That is what the major ultimate aim. For the deriving inductance Lx, so what is the need? What has to be taken into account? So Lx is the inductance of conductor X. That is going to be psi X. Psi X is the flux linking conductor X and current flowing through conductor X. This is what I would like to convey. Right? Now, so before moving to that, I would like to give you a few more introduction. Let me assume that the value of current flowing through conductor Ix is assumed to be Ix. Can anybody say what is the value of current flowing through X dash? Ix, exactly. So it is a parallel connected transmission line. Whatever the current flowing through X will be flowing through Ix, X dash also. Right. Let me assume that the current flowing through Y will be Iy. What is the value of current flowing through Y dash? Iy. Good. So let me assume that the current flowing through Z will be Iz. What is the value of current flowing through Z dash? IZ. Very good. Right. Now, if you look at this, there are 6 number of conductors. Each and every conductor is carrying a current. That currents will produce a magnetic flux, and that flux will link with conductor X. That is what the first point I would like to give you. So, the conductor X itself will produce its own flux. Then Y will produce a flux which will link with X. Current through Z will produce a flux that will link with X dash. I mean again X. Z dash, current flowing through Z dash will produce a flux that will link with conductor X. Y dash will produce a flux that will link with conductor X. X dash will produce a flux that will link with conductor X. So these are the things we are going to look into that. So for deriving that, I'm going to list out certain distances between the conductors. Let me assume that the distance between conductor X and Y is assumed to be D. So this is for the derivation purpose. Similarly, Y and Z is assumed to be, Y and Z is assumed to be again D. Similarly, the distance between conductor X and X dash is assumed to be N. Assumed to be N. X and Y dash is assumed to be M. X and Z dash is assumed to be H. Right? So now this is a position of 1 and the conductors are arranged like this. So these distances are measured for estimating the inductance. Now similarly, draw the position 2 diagram. So just look at this. This is position 1 and transpose the conductors and draw position 2. So transposition in the sense, so X is here, so X will take this position in the next one. So Y is here, Y will take this position. So Z is here, Z will take this position. Similarly, Z dash is here, Z dash will take this position. Y dash will take this position, X dash will take this position. So transpose the conductors and draw the diagram for position 2. So transpose the conductors, draw the diagram for position 2. So by doing this a transposition, you will get a position like this. So you may think that this is also possible, okay? Whatever I have explained here for the conductors in this manner also it is possible because the conductors are identical in nature. Here I have done it in the reverse way. That is, you can look at this. So X dash to here, Y dash to here, and Z dash to here. Okay. Anyhow, some convention you follow, that's it. Some convention you follow, the notation you follow, that's it. So now, in the first position, if you look at this, X and X dash, that is same phase conductors take this position. Second convention, it is taking this position. Third convention, if you draw it, the third convention is going to be this one. That's it. In the same fashion, if you look at the Y conductors, so Y first it is taking this position, second this one, and third this one. Similarly, look at Z position. So Z position, it is taking, this is first one, second one is this, so this is third one. So all conductors will have a same structural arrangement, right? Now with this, now I am going to derive the expression for inductance in conductor X. I am going to concentrate only on this. So if I am able to estimate the inductance of this conductor, I can easily evaluate anything. That is what the thing. So what I'm going to do is that I'm going to evaluate the inductance of this conductor. It is assumed to be Lx. Right? We all know that current flowing through conductor X and X dash is assumed to be Ix. The current flowing through Y and Y dash is assumed to be Iy. The current flowing through Z and Z dash is assumed to be Iz. Right. Now, if you look at this, what I'm going to do is that I'm going to evaluate the inductance due to the current flowing through conductors, all the conductors I'm going to evaluate. So, so let me move on to the step-by-step procedure. Before that, I would like to inform you a few more things. You can look at this. The conductor, first conductor is arranged like this. Let me assume that you may have clarity. So for about some distance, it is taking this position and it is taking next position. And for about some distance, it is traversing. Then again, it is taking another position. So that is what the transposition says that. So you have to assume that. So what it is meaning, say for example, from Karaikal to Pondicherry, one transmission line is there. So this is, let me assume that Karaikal line, Karaikal. And this is Pondi. Right? So the transmission line is transposed at regular interval. So Karaikal, it is taking some position. Then in between again one more position it is taking, that it may be considered as Chidambaram. So Chidambaram, the line is transposed. Got my point? So this is what it says that. So from Karaikal, first it is traversing and there is a transposition in Chidambaram. Then it is again traveling till Pondicherry. Again it is transposed to another position in Pondicherry. So this is what it says that. Similarly, if you look at Y. So first in Karaikal, it is taking this position and it is traversing. Another position it is taking at Chidambaram and it is traversing. And again it is taking another position at Pondicherry like this. Okay. So with this introduction, let me move on to that. So major two advantages I would like to specify. First one, you may take down, a double circuit three-phase line has two parallel conductors for each phase. Right? The use of two three-phase circuits on the same towers leads to a greater reliability and a higher transmission capacity. So reliability in the sense, if any one of the conductor is in fault condition, another conductor can be utilized for transmitting the power. So greater reliability in the sense, if any one of the conductor is in fault condition, that is, you all know that for R phase, X and X dash are responsible. And if any one of the conductor is damaged, that is, if X is damaged, you can use X dash for transmitting the power. So this leads to greater reliability. Similarly, since it is using two conductors, the transmission capacity of the line will be more. So with that, I'm going to move on to derivation. So you all know that the inductance, I'm going to concentrate on the conductor X alone for calculating the inductance. So for that, I'm going to estimate the flux linkage associated with that conductor. So let me start with the first one. Flux linkage of conductor X in position number 1. So I have taken a position number 1. So refer the previous derivation and tell me what is the flux linkage of conductor X in position number 1. That is, so flux linkage can be due to its own conductor and flux linkage can be due to the current flowing through conductor Y. Flux linkage can be due to the current flowing through conductor Z. Similarly, the flux linkage can be due to conductor current flowing through conductor Z dash, Y dash and X dash. So all these will contribute for the flux linkage. So now tell me what is the expression for flux linkage at position number 1. Yes. Yes, good. Good. 1 by H. Good. Good. Yeah. Good. Very good. Very good. Very good. So firstly, the current flowing through this will create its own flux linkage, that is 2 into 10 to the power of minus 7 ln, so Ix ln 1 divided by R dash. R dash is a conductor X resistance, self resistance. This is first. Then there is a current flowing through this Y. That Y current flowing through this Y is assumed to be Iy. So this will create a flux linkage, that it is 2 into 10 to the power of minus 7 Iy ln 1 divided by distance between the conductor Y and X, it is going to be D. Similarly, if you look at this, the conductor Z, there is a flow of Iy current that will create a flux that will link with this conductor X. So that expression is going to be again 2 into 10 to the power of minus 7. Current is Iy ln, sorry, Iz ln distance between conductor Z and X is, this is D. This is again D. So D plus D, it is going to be 1 by 2D. 1 by 2D. Right? Similarly, now coming to this next one, Z dash. Z dash, the current flowing through Z dash is Iz. That will produce a flux and it will link with conductor X. So then, if you look at the flux linkage expression, 2 into 10 to the power of minus 7, current is Iz ln the distance between conductor Z dash and X is assumed to be H. So 1 divided by H. Similarly, the current flowing through this y dash will create a flux. The current flowing through this y dash is assumed to be IY. That will create a flux which will link with conductor X. So if you do the flux linkage expression, 2 into 10 to the power of minus 7 IY ln distance between y dash and z is assumed to be m, 1 divided by m. Similarly, next to last conductor X dash, there is a flow of current Ix that will produce a flux which will link with the X. So that we are looking at 2 into 10 to the power of minus 7 Ix ln 1 divided by distance between X dash and X. It is assumed to be n. Right? So by doing this, if you derive the expression, you will get an expression. You just check this expression. The common terms Ix, Iy and Iz alone, I have taken it out. So any clarification on this? Any doubts? So anybody is having doubts?
No, sir.
Right. Now what we have estimated is that flux linkage of conductor X in position number 1. Position number 1. So there are 3 positions it is taking. First one Karaikal, then Chidambaram, then Pondicherry. 3 position that conductors are transposed. So the position number 1 alone, we have estimated the flux linkage. So the second position I'm going to move on. So take down flux linkage of conductor X in position number 2. So for deriving that, I'm going to take the position number 2. Right. Now I will ask you people one by one. So can anybody say what is a flux linkage of conductor X due to its own current Ix? Can anybody say roll number Bhavya, roll number 13. Bhavya is there? Just try once.
Yes, sir. 2 into 10 power of minus 7
2 into
Ix
10. Good.
Ix ln 1 by
Ln
r.
1 by r dash, because it is the same conductor. Am I correct? Yes, good. So one more thing. Just wait. Right. So first we have assumed this conductor, the current flowing through this conductor. Now let me assume that I am going to look at Y. There is a flow of current Iy in conductor Y that will produce a flux and that will link with conductor X. Am I correct? So by assuming that, can anybody say what is a flux linkage at conductor X? Roll number Ilandiran. So just it can be tried. Ilandiran is there? Bhuvana. Bhuvana. Bhuvana is there. So Bhuvana is there. Ilandiran is there. Ilandiran is there. Bhuvana. So is there, or everyone is just switched on and left? It's a very good thing actually. Actually, everyone is there or just connected?
We are there.
Huh?
We are there.
Abhik is there? No. Abhik, Akshun, Bhuvana. Shall I take the class or shall I leave? Santosh is there. Yes, Bhuvana. This much time I am calling. Kritika is there. Shall I continue or we'll see it in another class? Because I think no one is there.
Continue, sir.
You can continue.
If no one is there, it is better to, I mean, whoever is present, that people can alone present. Why connecting and sitting idle? Am I correct? Abhi? Snehalata is there?
Yes, sir.
Okay. Ilandiran just connected, I think.
Hello, sir.
பா தம்பி இவ்வளவு நேரம் கூப்பிடுறேனே ஒரு தடவை ரெஸ்பாண்ட் பண்ணலாம்ல
Sir, sorry, sir.
நெட்வொர்க் கனெக்டிவிட்டி கம்மியா இருக்கா
Sir, no, sir. Sir, I went to hospital, sir. My sister got positive, sir. So,
அப்படின்னா கனெக்ட் பண்ணாமே இருக்கலாம்ல
I just recording, sir. That's it.
அட்லீஸ்ட் சொல்லலாம் okay okay shall I continue or shall I go ahead that is why I am not at all actually I wanted to be interactive with you people generally as if no it is a general thought everyone is connected and if you are doing some other work so better not to connect I won't ask you you have to be you have to connect it for the class okay even if you are not connected I won't bother about that okay so if you are connected so please be attentive and just connect and leave I mean it will irritate sometimes that is why I'm not calling you people in the class generally okay so better is that if you're connected be attentive or otherwise don't connect it I won't bother about anything so if you're not connected I won't bother about that okay so anyhow so if you look at this so at position number 2 if you derive the expression for flux linkage you will get an expression like this verify this expression
Yes, sir.
so the concepts whatever we are learning right now for me it took a large amount of time for understanding itself no it is not so simple in what sequential manner I have to follow so that the students will be able to understand very easily something like that I'm following certain procedures and for me also it took large amount of time for the understanding itself okay and I mean once you're going through the book or textbook without attending the class definitely I'm of the opinion that understanding the concepts will be very difficult right now position number 2 is completed now let me move on to next one so flux linkage of conductor X in position number 3 so for deriving the expression for flux linkage of conductor X in position number 3 I have taken a position 3 conductor arrangement and I have drawn it here So now position number 3, if you are evaluating the flux linkage, you will get an expression like this. That is position number 3, X is taking here. So there will be a flux linkage due to its own current Ix. So that it accounts for ln 1 divided by R dash. Right. Similarly, X dash is present. There is a flow of again the same current Ix. So that contributes for that is distance between X and X dash is, say you can look at this, Y and Y dash is N. Hence, X and X dash is going to be again N. So that is the reason why it is made it as ln 1 by N. Right. Now coming to the next one. So there is the conductor is X. There is a flow of current IY in conductor Y and Y dash. That will create a flux here. Y and Y dash. So for Y, the distance between conductor Y and X is assumed to be 2D. That is the reason why it is here, it is ln 2D. 1 by 2D. So D plus D, it is going to be 1 by 2D. So the distance between X and Y dash is assumed to be here Y and X is H dash, the same distance here again H. So that is why the second time it is ln 1 by H. Right. Similarly, so conductor X is the assumed conductor. There is a flow of current Y in Z and Z dash that will create a flux which will link with X. So that if you look at this, the distance between Z and X is D. Z dash and X is M. Z dash and X is M. So if you look at this, ln 1 by D, ln 1 by M. Right. Now we have evaluated. The flux linkage at 3 different positions. That is, the transmission long transmission line is there. It is transposed at regular interval, and 3 different positions the conductor is taking. So at that positions, I have evaluated the flux linkage. Now it is time to evaluate the average flux linkage of conductor X, the average flux linkage. If I am able to evaluate the average flux linkage, then I will be able to evaluate the inductance very, very easily. So the first step, the average flux linkage of conductor X is psi. If it is assumed to be psi X, it is going to be psi X1 plus psi X2 plus psi X3 divided by 3. So psi X is equal to psi X1 plus psi X2 plus psi X3 divided by 3. Substitute psi X1, psi X2 and psi X3 in expression number 4. So substitute and simplify it. Substitute and simplify it. So if you are substituting and simplifying it, you will get an expression like this. Mathematical simplification, just a mathematical simplification. So no conceptual things. Substitute psi x1, psi x2 and psi x3 from equation number 1, 2 and 3. Then if you are simplifying it, you will get an expression like this. That is 2 into 10 to the power of minus 7 ix ln 2 power 1 by 3 d by r dash m divided by n the whole power 2 by 3. So now we have evaluated the average flux linkage psi x. Now it is time to evaluate Lx. So Lx is equal to psi x divided by Ix. Psi x divided by Ix. So by doing that, now Lx is psi x divided by Ix. So if you are substituting, you will get Lx will be equal to 2 into 10 to the power of minus 7 ln 2 power 1 by 3 d by r dash m by n the whole power 2 by 3. So now, so Lx is the inductance of conductor X. Conductor X. So there are two conductors per phase, X and X dash. These two conductors are connected in parallel. These two conductors are connected in parallel and are assumed to be identical in nature. Identical in nature. Hence, the per phase inductance of the circuit will be equal to the conductor inductance divided by 2. That is going to be the per phase inductance. So you may take down inductance of each phase is equal to 1 divided by 2 inductance per conductor. Inductance per conductor. That is inductance per conductor is equal to Lx. Lx. So that if you are substituting it, you will get an expression like this. Just verify the expression. Inductance of each phase is equal to 2 into 10 to the power of minus 7 ln 2 power 1 by 6 d by r dash the whole power 1 by 2 m divided by n the whole power 1 by 3. So this is a final expression in inductance of a double circuit 3-phase line. Double circuit 3-phase line. So this you should remember. So now what I would like to convey here is that now you people are very much familiar in estimating the inductance of a various circuit. So we have started with simple conductor, then single phase line, 3-phase, 3-phase symmetrical, 3-phase unsymmetrical, 3-phase unsymmetrical with transposed conductors, 3-phase double circuit unsymmetrical with transposed line. So these are some of the estimation procedure. These you people have to know about this, right? In the similar fashion, now we are going to move on to the next topic called capacitance estimation. Capacitance. So one may think that so transmission line is just a 2-conductor where the capacitance effect is coming into picture. Everyone may have a thought on that. Am I correct? So though it is just 2 conductors are running in parallel, in between there is an air act as an insulating medium. So there are 2 conductors in between air air act as the insulating medium. Hence, the conductors along with air can create a capacitance effect. So, how to estimate this capacitance, that we are going to see it in the next class. So, beginning, only one thing I would like to specify here. So, the capacitance estimation, you all know that. Can anybody say what is the expression for capacitance in terms of the charge carrier and the potential difference? Can anybody say you would have learned it? Which one? C equal to Q by? Okay. C equal to Q by V. Q by V. Okay. Right. Now, the important thing is that here, any conductor, if you know the potential difference in the conductor, you will be able to easily evaluate the capacitance in the system. Capacitance in the system. The potential difference evaluation is the important thing with respect to the capacitance calculation. In inductance calculation, I said that flux linkage. Flux linkage. Here, potential difference. If you know potential difference, it will be you can easily evaluate the capacitance. So the potential difference between 2 points can be estimated with the help of the electric field intensity. Electric field intensity. Generally, electric field intensity is represented with a symbol called E. Wherever you are seeing E, that you can immediately say it is electric field intensity. So H here represents the magnetic field intensity. Similarly, E represents the electric field intensity. If you know electric field intensity, you will be able to easily identify what is the potential difference between 2 points. That we can easily estimate. So that we will see it in the next class. Thank you very much for listening to this class.